Chapter 5. So we're moving on to Chapter 5, which focuses on stereochemistry at tetrahedral centers. So let's discuss a little bit. So first, let's review. So constitutional isomers have the same molecular formula and a different connectivity of atoms. So for example, we have 2-butanol versus 1-butanol. Same formula, different connectivity of atoms. Organic chemistry is often very concerned with the idea of stereoisomers, which have the same connectivity of atoms, but with a different 3D and spatial arrangement of atoms. So we've already seen examples of stereoisomers even in our general chemistry course with alkene stereoisomers, where the cis stereoisomer has the substituents on the same side of the alkene, while the trans isomer has substituents on opposite sides of the alkene. We also have observed cis and trans isomers in cyclohexane. Remember, for a cis cyclohexane system, substituents are on the same face of the ring. So notice both of these methyls are pointing up. They have the same stereochemistry. While the trans cyclohexane, we have our substituent on opposite faces. They have the opposite stereochemistry. So we've seen stereoisomers already in the previous chapters and even as recently as chapter 4. So we have the same connectivity of atoms, but a different three-dimensional shape. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions so far? Okay, so let's keep going. So let's talk a little bit about chirality. Let's talk a little bit about chirality and the principles that underlie this idea of chirality. So if you look at your hands for a moment, you notice that each hand is the mirror image of the other hand. These mirror images are non-superimposable. Many organic molecules have non-superimposable mirror images that result from substitution patterns on an sp3 hybridized carbon. Chiral molecules contain non-superimposable mirror images and by definition lack an axis of symmetry. So if we look at our left and right hand, for example, just like our hands are non-superimposable mirror images, in many cases we have organic molecules where as the result of substitution at our sp3 hybridized carbon atom, we end up with two unique structures that are non-superimposable mirror images. And we call enantiomers a pair of molecules that are non-superimposable mirror images. So just like our left and right hands are enantiomers of each other, they're non-superimposable mirror images with the same formula and same basic connectivity of atoms, molecules that exist as a pair of non-superimposable mirror images are known as enantiomers. So these two drawn structures are enantiomers of each other. They're non-superimposable mirror images. Let's look at another example for enantiomers. If we look at the following substituted carbon, we notice that if we compare the three-dimensional arrangement of each of our substituents, we notice that our two structures on the left and on the right are mirror images. Let's make a model of each of these two structures, and then let's discuss and let's analyze these two structures in detail. So give me one moment to put together the models for these two structures, and let's show that in fact these two molecules are non-superimposable mirror images, that these two molecules are enantiomers. So I'd like you as well to follow along with your own model kit, and I would recommend that you also put together a model of this structure. So that way you can more easily visualize and identify that these two structures and these two compounds are enantiomers of each other. So we're still putting together the model for this structure. And what we're going to do is we're going to observe each of these structures, and we're going to try to determine whether or not these mirror images are superimposable to each other. Okay, so we have our two structures. As you notice, these two structures are mirror images of each other. Does everyone see that in the camera, that these two structures are mirror images of each other? Now, if we rotate and we try to superimpose these two structures, so if we rotate and we try to superimpose these two structures, we run into an issue. We notice that no matter how hard we try, these two mirror images are non-superimposable. We have different substituents at different positions in 3D space. So as a result, we conclude that these two compounds, these two chemical species, are enantiomers of each other. So these two compounds are enantiomers. They're non-superimposable mirror images. So let's try to determine the criteria for what makes a molecule chiral and what makes a carbon center a chiral center. So a lot of what we're going to be doing in this chapter focuses on analyzing molecules to determine the chirality based on an axis of symmetry and the position and type of our substituents. A chirality center, also known as a chiral center, stereocenter, or stereogenic center, is known as a carbon with 4 different substituents. So a carbon center with 4 unique substituents. Now, a molecule that contains chiral centers with no axis of symmetry is known as a chiral molecule. The easiest way to visualize chiral molecules is to build molecular models to help visualize your enantiomers. So let's look at an example. So let's look at what happens. Let's look at what happens when we look at a carbon with only 2 different substituents. So let's look at the compound and its proposed enantiomer, and let's see whether those 2 compounds are genuinely enantiomers, whether we genuinely have non-superimposable mirror images. So give me one moment to put the models together, as this really is most easily visualized using your model kit. Okay, so we have our two proposed enantiomers. So we've attempted to draw their mirror images. My question to all of you is, when we overlay these two structures, are these two structures superimposable? Are these two structures superimposable? Do our substituents match at every position? What does everyone think? Are these enantiomers superimposable? Yes or no? Don't be shy to share your responses in the chat or verbally. What do we think? Are these two enantiomers superimposable? Can we overlay them and exactly match all of our substituents? Yes, right? So in this case, if we were to draw out our structure and its proposed enantiomer, we notice immediately that these two structures, even though they were suggestively drawn as if they were mirror images, these two structures are representing the same molecule. These two structures are identical. Let's look at what happens when we add another substituent to the mix. Let's look at what happens when we add another substituent to the mix. You may think, well, that's going to make a pretty big difference. Well, let's see. So in this case, we have our two proposed structures. So I've made a model of both of these structures, and I'd like to hear your perspective now. Do we think these structures are superimposable or non-superimposable mirror images? And to help you along with that, if we rotate this molecule, now my question is, are these molecules identical or different? Are these molecules the same or different? We try to overlay them. Do our substituents match at every single position? What does everyone think? So we have in our discussion that I see in the chat, a lot of students are saying that they're the same. That's exactly right. So because this carbon does not have 4 unique substituents, when we tried to draw its mirror image, we notice that these two mirror images are representing identical compounds. Finally, let's look at a carbon with 4 different substituents. Let's look at a carbon with 4 different substituents. If we try to look at its mirror image, if we try to look at its supposed enantiomer, let's look and let's see if these structures truly are non-superimposable mirror images. Okay, so I've made a model kit of these two structures. And let's try via rotation to line up these two structures. So I've lined up my purple substituents And now my question to all of you is, when I try to overlay and superimpose these two molecules, are these mirror images superimposable or non-superimposable? Are these two molecules the same molecule or enantiomers? What does everyone think? Are these the same molecule or enantiomers? We try to overlay them. We notice that they don't superimpose on each other. So are these molecules the same or are they enantiomers? So we see in the chat that they're non-superimposable mirror images, and so the chat concludes that these compounds are enantiomers. Exactly right. These two mirror images are non-superimposable, and these two structures represent two unique enantiomers. Non-superimposable mirror images. In general, a carbon is a chiral center if it has 4 different substituents and the molecule itself is chiral if it lacks an axis of symmetry. Does that make sense to everyone? Okay, so let's keep going now. So what we're going to talk about next is we're going to look at the process for rotating molecules and ensuring that our two and checking that our two compounds are superimposable. So we can do this very easily with a model kit, and I'm going to show you now how to do this exact same process with a pen and paper. Okay, so we have our two molecules. The bromine in purple is on the top, the fluorine in yellow is on the bottom, and the chlorine in blue is also on the bottom. Okay, so suppose we have two structures and we want to check that these structures are enantiomers or identical. So we're going to keep one structure exactly the same. So I'm just going to draw the structure as is. So if we look at this structure in detail, the trick for drawing out these dash wedge notations is any substituent with a wedge is pointing out towards us. So does everyone see how this fluorine is pointing towards us? Does everyone see how this fluorine is pointing towards us? And that's why we give this a wedge. Okay. Likewise, any substituent that is pointing away from us in the back, such as this hydrogen, is given a dash. We make sure that one of our set of carbon substituent bonds is flat within the plane of the page. So we draw our bond to bromine, our bond to chlorine with just a normal straight line. Okay, so now that we have our first structure, let's look at our second structure, which is a little bit more interesting. So starting off, following our dash wedge notation, we have our bromine. We have our fluorine pointing out towards us, and our hydrogen in the back. Except this time our chlorine, so our fluorine is pointing out towards us on the left-hand side, our hydrogen's in the back, and our chlorine this time is pointing in the opposite direction to the right. Now, in order for these two structures, in order to propose and try to overlay these two structures, what we're going to do what we're going to do is we're going to rotate our bottom substituents clockwise, essentially exchanging the position of all three of our substituents. So to show you how this works with a model kit, what we are doing is we are just rotating our model, and then we are drawing whatever we see after rotation. So after rotation, we have our bromine pointing up, our chlorine pointing to the left. This time, our hydrogen is pointing out towards us, and our fluorine is in the back away from us. Does everyone see that from this model? Does everyone see where I got this new depiction after rotation? Okay. Now, for comparison, it's really important that you want the same quote unquote backbone. So you want to make sure that your flat substituents, your substituents that are in the plane of the page are pointing in the same direction. And now what we can do is we can very easily compare the position of our substituents. As we can see, our substituents are all in different positions. So these two compounds are non-superimposable. And as a result, compounds A and B are enantiomers. So does everyone understand how to do the rotations that we've done with a model kit on paper? So what we've done is we started out, sorry. Here we go. So we started out with the following structure. All we did was rotate our molecule so that our substituents in the plane of the page were pointing in the same direction in structure A and B. Then we look and see, how do our substituents pointing out of the page and into the page compare? Are our two structures superimposable? As we notice, if we compare our two structures, we notice that these two structures are non-superimposable mirror images. And as a result, these two structures are enantiomers. Does that make sense to everyone? Does this idea between connecting what we've done with the model kit and what we're doing on paper make sense? Perfect. Okay, so let's keep going now. And there's one other topic that we need to discuss, and this is the idea of a plane of symmetry. Molecules that have a plane of symmetry that divides the entire molecule into two pieces that are exact mirror images are achiral. Molecules with a plane of symmetry are achiral. A plane of symmetry is a vertical or horizontal axis that results in identical substituents on both sides of the axis. If a molecule has an axis of symmetry, the molecule is achiral. So let's take a look. Let's take a look at some achiral molecules. So in this first structure, we have a bromine with a wedge. And as we notice, we can cleanly bisect this molecule into two pieces which are identical on each side of our plane of symmetry. So as a result, this molecule is achiral. Another way that you can think about this is simply if we think about the substituents attached to our bromine, we essentially have quote unquote identical substituents. it's another way of thinking about things that makes it a little bit easier to understand this idea of a plane of symmetry. So to show you what this looks like in a model kit, so if we look at our structure from a top-down perspective, what we see almost immediately is that this molecule is perfectly symmetrical. We can draw a clear axis of symmetry bisecting our molecule. Does this make sense to everyone? This idea of an axis of symmetry? Molecules with an axis of symmetry are considered achiral. Let's look at another example. In this case, we have a carbon with 2 hydrogen substituents. Now, if we draw out and we look at a model for this structure, we can immediately notice a plane of symmetry in this molecule. So let's take a look at this structure. So here we go. So we have our tentative structure, and we can easily draw a plane of symmetry after rotation where we cut the molecule vertically. And does everyone notice how if we cut the molecule on this plane of symmetry, our 2 substituents on both sides of our plane of symmetry, our 2 hydrogens are identical? Does everyone see how the 2 hydrogens are identical? If we cut this molecule on its plane of symmetry, does everyone see how this molecule has a plane of symmetry? How it has 2 identical substituents and a clear axis where the substituents on each side of the axis are identical. So just to showcase that once again, so we can clearly draw a vertical plane of symmetry that separates and that bisects our molecule. And as we can see, both of our substituents on the opposite sides of our plane of symmetry are identical. So as a result, this center is achiral. Now, one thing that we have to really be careful about is that when we deal with sets of adjacent stereocenters, we have to make sure that our substituents are exactly identical. So for example, after rotation, we can draw this molecule as something like this. Now, depending on the stereochemistry, we either have a clear axis of symmetry where our 2 mirror images, where our mirror images are non-superimposable, or our molecule lacks an axis of symmetry. So let's look at 3 cases. And let's try to determine whether or not an axis of symmetry is present. Okay, so here are 3 cases, and this will be the last example that we deal with today. But this is a very important example as it highlights the fact that the stereochemistry at each of your carbons is critically important in order to identify the presence of an axis of symmetry. Okay, so let's look at each of these two molecules and let's try to determine which of these molecules possess an axis of symmetry. So looking at A, B, and C, just as a first guess, so for A, B, and C, which molecules would you expect would have an axis of symmetry? Which molecules would you expect to contain an axis of symmetry? Just your first impression, your first guess. Which of these structures, which of these molecules would you expect to be genuinely chiral? And I'd like you to start putting together your model for this structure. Okay, so let's look at structure A. So in this case, we have our carbon skeleton and both of our alcohols are pointing out of the page. So looking at this structure, does it possess a clear axis of symmetry? Does this structure possess a clear axis of symmetry where our substituents are identical on each side of our axis of symmetry? Yes, so we have students proposing that A and C possess an axis of symmetry. So looking at structure A, we see the clear presence of an axis of symmetry. And as a result, this molecule is achiral. It can also be considered a meso compound. We'll talk more about what meso means later on in this chapter, but simply it means it's a molecule with chiral centers that possesses an axis of symmetry, in turn making the molecule achiral. Now, if we look at structure B, now, in this case, for structure B, do we see the same axis of symmetry? Do we have the same axis of symmetry at play in structure B? No. As we can clearly see, the relative position of our alcohol substituents is different, so this molecule is chiral. There's no axis of symmetry. Finally, and now we can prove this to ourselves. So what I'm going to do is I'm going to make a model kit of the enantiomer of this structure. This is the way that you can check your work. You can verify that your assignments are correct. So let's make a model of the enantiomer. Give me one moment to put everything together. Sorry about that. The model kit was blocking the camera. So let's build and let's showcase the enantiomer. And if this molecule truly was chiral, then we would not be able to superimpose the structure with its mirror image. So let's make the mirror image, and then let's see what we can see. Okay, so if we look at this structure's mirror image, if this structure is chiral, then the structure and its mirror image should be non-superimposable, and there should be no axes of symmetry present. So if we compare our two molecules, our two enantiomers, we notice immediately that the structure and its enantiomer, no matter how hard we try, are non-superimposable. Additionally, we notice that there's no axis of symmetry present in this molecule. No matter how hard we try, the substituents and the position of our substituents on both sides of our axis of symmetry are different. Does that make sense to everyone? Does everyone see why B is chiral while A and C are achiral? Okay, so that's it for today. We'll save this last example on this page for our follow-up lecture during the laboratory period. So what we're going to do is we're going to wrap up today's meeting.